So I'm going to talk about graphs and the algorithms that you're commonly going to encounter related to graphs. So just a quick introduction to graphs. A graph is a data structure that has nodes, also known as vertices, and edges which connect the nodes. They're used to represent relationships between objects and networks or paths, etc., depending on what situation you're in. So we have a few different types of graphs. So we have directed graphs, which are graphs where the edges have a direction, where A is connected to B, but B is not necessarily connected back to A. I have a diagram here showing that 1 is connected to 2, but 2 isn't connected back to 1. So that's a directed graph. And undirected is just the opposite, where you don't have a direction. Like that one up there, A is connected to B and B is connected to A. And then we have weighted and unweighted graphs. So weighted graphs are graphs where the edges have a cost or a weight to them. So I have an example of a weighted graph up there where the connection from A to B costs 1 and the connection from A to C costs 3. So depending on what situation you're in, you're going to want to implement a graph in a different way. So for example, if I have different cities A, B, C, and D, and the distance between A and B is smaller than that between A and C, I don't want them to have an equal weight because it costs more to travel those different distances. So how do we actually represent graphs in code? I'm going to give C++ examples and Python examples. So the most common one for competitive programming is going to be an adjacency list. So each node has a list of other nodes that it's directly connected to. This works well for graphs where there's not a whole lot of edges. This is called a sparse graph because it will take up less space. And it's very fast for iterating over the connected nodes because for each node you have a list of all that it's connected to. So if I need to quickly get all the neighbors of a specific node, this is really helpful. And like I said, it's ideal for most competitive programming solutions because it's going to be a lot more efficient than this next one that I'll talk about, which is an adjacency matrix. So this is the other main way of representing a graph, is a 2D array where you have each dimension is how many nodes you have. So if I have node 1 and node 0, because we're 0 indexed here, right? I think I have a laser pointer here. That would be that object in the matrix right there, and that 1 indicates that there is a connection between node 0 and node 1. These are better for dense graphs where there's a lot of connections because checking a connection is as simple as just checking the value at the 2D matrix of where the edges or where the nodes are connected. So if there is a connection there, it's going to be not 0. In this case, I'll have all 1s, but you could use any number other than 1 to represent a weighted graph. So yeah, like I said, it's best for dense graphs because it's going to be an adjacency list is going to have a lot more space taken up if you have a lot of edges from one node, whereas this is going to be the same amount of space no matter how big the graph is because you have to allocate a n by n matrix. But that also means that if you have 1,000 nodes in your graph, your matrix is going to be 1,000,000 blocks wide, right? And that takes up a lot of memory, and you only have a limited amount of memory to work with. So in general, this is not the one that I choose to implement, but it can be good for certain things. So choosing the representation, how do I know which one I should do, right? So like I talked about a little bit, an adjacency list is going to be better for sparse graphs with not a whole lot of edges because it will save memory. It's going to be better for certain algorithms where you need to iterate over all of the connections of a single node. And an adjacency matrix is going to be better for when you just need to know if 2 nodes are connected directly because that's a constant lookup time. It does have high memory usage like I explained, and it's going to be a little faster for checking, but I still, like I said, I implement an adjacency list more often than I implement an adjacency matrix. So depending on the actual problem you're given, you'll want to choose either the matrix or the list. So when you have a large amount of nodes, like I said, you don't want to have to um, allocate a matrix, a 2D matrix, where each dimension is how many nodes you have. Because if I have 1,000 nodes, like I said, that's 1,000 times 1,000, which is um, a million like space to allocate. Um, but if I need to make a quick edge like check between two nodes, it's always going to be faster to do it in a adjacency matrix because it's just constant lookup. I just look if there's a value at the block that I'm looking at. Um, but for most other applications, an adjacency list is going to be better, especially for the algorithms we're going to talk about, because the algorithms that we use tend to rely heavily on iterating over neighbors of a node, which is really easy to do when you have an adjacency list. So I have just a example here of what types of problems you should in general, this isn't a specific, you absolutely need to use this implementation, but this is usually the idea that I go with. If I'm doing something pathfinding or checking if something's connected or I'm looking for cycles, I'm going to use an adjacency list. It's going to be a lot faster for that. But if there's a really, really dense network, or I need to do this algorithm for checking all of the shortest paths between all of the pairs, which is a really heavy algorithm, it's going to be a lot better to use something like an adjacency matrix, but that's sort of more of an edge case. So talking about the actual algorithms, we're going to talk about depth first search. Has anybody heard of depth first search here? Okay. Yeah, it's a pretty common one. It's probably one of the first ones you're going to learn in um, like a data structures class or a comp sci 2 class, depending on where they want to teach it. And you'll also learn about it probably in your discrete class because it's a pretty simple way of traversing a graph. So I have a little GIF here on the right that's going to demonstrate the actual process, and I'll explain it. So it explores as far as possible along one branch, and then it backtracks. So it traverses one path all the way to the end, then goes back and keeps traversing. So in this case, it's going to go all the way down the left side, then all the way down that one, then all the way down until it traverses all the way through. And this is very useful for problems where you need to find paths between nodes. If you need to detect cycles, or if you need to find connected components, because again, this is going to be finding a cycle is going to be a lot faster because cycles only happen when you have a full path that connects back to itself. So this is going to be very fast for finding cycles. So how it works might be a little hard to read those. The actual code itself doesn't matter all that much as long as you understand the process and you can write it. But you can use a recursive approach, which is generally what I use, as long as there's not going to be a lot of iterating going on. In general, you're going to have enough recursion depth to be able to do these. So in my Python program here, I define a set of visited nodes, and those visited nodes are going to be obviously the nodes that I've visited already. And then for all of the neighbors in my current node, if the neighbor is not already in the visited, I'm going to search along that path. Pretty simple algorithm. It's only 5 lines here. So, yeah, that's a pretty simple algorithm. It's really helpful for a lot of stuff though. Yeah, so the applications, cycle detection, determining if a graph has a cycle is something that you're probably going to have to do, not just in competitive programming, but like in other various things for your classes. Then also counting connected components. In some cases, the problem's going to give you a graph, but not necessarily all completely connected. I might have A and B connected over here, but they're not connected to anything in the rest of the graph. And so determining if you have connected components is an important part of determining which algorithms you have to use. So using depth first search to do that is going to be helpful. And yeah, like I said, finding a path from A to B. This is exactly what this is made for. So the time complexity, without getting too deep into it, it's just going to be the number of vertices plus the number of edges because you have to iterate over all of each of those. And the space complexity, it depends on how you implement it and how how the graph is set up is how deep you're going to recurse into it, but it can be O of how many vertices you have for the recursive calls. That's like the worst case. So breadth first search, like depth first search, you're going to be doing this for traversing graphs, but it's a little different process. I have another GIF here to show the process, but basically, as opposed to depth first search, where you search all the way down a single branch, you're going to start at a node and search all of its neighbors one layer out. And then for each of those neighbors at that layer, you're going to search all of those, all of the next layer, basically moving layer by layer until you have the entire graph searched. This is useful for finding the shortest path in unweighted graphs because the layered approach makes it easy to detect when you're actually at the shortest path without having to do a lot of extra work. Because if I'm only searching 2 layers deep and I've already found my node, I know it's only 2 layers away. So how it works, it uses a queue to keep track of the nodes to visit next. So does anybody know what a queue is? Well, a queue uses something called first in, first out. It's like a line. If you think about lining up for something, whoever goes in first is the first out. And then if you go in the back, you have to wait for everybody in front of you to go out first. That's exactly how a queue works. So it processes it in that order, ensuring that it's going to process all of the nodes at the layer before it moves on to the next layer. So the applications for this, like I said, it's good for the shortest path because of the fact that you're finding all of them at a layer and then going to the next layer and then going to the next layer. So once you find the actual node you're looking for, you know you found the shortest path. It's also good for connected components, but what I primarily use it for is stuff like flood fill, where I need to take an area of a graph and fill it like it would be if you poured a bunch of water on it, like a flood. So the flood fill algorithm is for detecting if components are connected in a graph, and this breadth first search is really good for that because it feels exactly like you would if you had poured water on the graph. So the time complexity is going to be the same. It's going to be the amount of vertices plus the amount of edges, and it's also the same space complexity, but for kind of a different reason because you have to implement the queue. Yeah, you have to also keep track of the visited, like I said. I have the example code here. It's a little more complicated than depth first search, but it's not overly complicated. The most annoying thing is the fact that you have to keep track of a queue and you can't just do recursion. So it's a few extra lines, but it's a similar process. You're just popping from the queue, checking all of those neighbors, and then if it's not in the visited, it adds it. And then it keeps track to make sure that it's only visiting the one that was in first and not the one that was in last. So one big algorithm or type of algorithm you're going to want to know is how to find the minimum spanning tree of a graph. So does anybody know what a tree is in a graph? Yuri?
It's connected and it has no cycles.
Mhm.
And I think there's one other property.
I mean,
It's a graph that's connected and no cycle.
yeah, that's pretty much the extent of a tree. Yeah. So if I have a graph with a bunch of nodes, finding the minimum spanning tree. So minimum means lowest cost. Spanning means it uses every vertex or every node, and tree means there's no cycles in it. So finding that is going to be really helpful for certain problems, which I'll explain. It's a subset of edges in a weighted connected graph that connects all the vertices with the minimum possible total edge weight, basically. So you're summing up all of the weights in this new spanning tree, and also no cycles because it has to be a tree. So a couple key algorithms. The text is a little small there. You're probably going to learn these in your data structures class, but a couple of the algorithms are going to be Prim and Kruskal's. They have different processes, but they end up giving you the same answer for whatever tree you give them. So they're pretty much going to be, it's just going to be up to you which one you want to implement. I'd say Prim is a little easier to implement because Kruskal's requires some extra working to check if it's already connected to the graph. Because in Prim, all you do is you just pick a starting node, and then you pick the lowest weight that's connected to that node, and then that new node that it's connected to becomes part of the tree, and then you just keep expanding it. So that's what this GIF is showing, is the minimum spanning tree. So it starts at B, and then the lowest weight from B is 1, then it connects it to A, and the lowest weight from B is 2, so it connects it to D. If I can restart the GIF here. So it's checking all of the connected edges. So it's checking that 3 that's connected to A and the 3 that's connected to B and the 2 that's connected to B and the 6 and the 5 and finding whichever one is the least, right? So it's a greedy algorithm choosing the lowest weight at whatever step you're at. And like I said, you're going to get the same graph for, you're going to get the same tree for either algorithm. So I'll just go through on this little graph here, Kruskal's and Prim's algorithm. So for Kruskal's, there's no starting node. You just sort all of the nodes or all of the edges in the graph by their weights. So first what I'm going to do is I'm going to find the lowest weight, which happens to be this one here. Is it going to write? Yeah. Okay. Happens to be that 1. And then the next lowest one is going to be the 2, and I can add that edge as long as it doesn't create a cycle, because again, we want it to be a tree, and trees have to have no cycles. So I'll add that 2. Then the next one is going to be the 3, and I can add that because it's not adding any cycles. And the next one is going to be the 4, because again, it's not creating any cycles. And that is the entire tree, because as you can see, every node is connected, and yeah, I haven't created any cycles, so that's the minimum spanning tree. And the process is going to be different, but the outcome is going to be the exact same for Prim's algorithm, where say I choose E as my starting node, I'm going to check all of the available edges, which in this case are going to be the 5 and the 2, and the lowest is the 2. Then I now have E and D in my graph, and I'm going to check for which has the lowest connection. So I'm going to check this 5, I'm going to check that 10, and I'm going to check the 4. The 4 happens to be the lowest, so I add that to my graph. Then I have E, D, and C in my graph. I'm checking the 5, the 10, the 7, and the 3, and the 3 is the lowest, so I add that to my graph. And then finally, checking all those edges again, the 1 is the lowest, so I'm going to take that 1. And we end up with the exact same tree as the Kruskal's, just with less effort, in my opinion. So, where are you actually going to use these? They're used for minimizing cost in like a system, right? So like a road system, if you want to visit all of the nodes in the road system, but you want to do it in the shortest amount of time possible, you'll find the minimum spanning tree and you can visit all of them. And it also is good for connectivity problems because it ensures the minimum connections, basically. It's a little complicated to implement in code, but I have a little implementation here of Prim's algorithm. The annoying thing is that you have to use a priority queue, which in this case I've called min heap, to keep track of which edges are available, and the priority means that it's always sorted by the lowest weight. This is actually the implementation I use most of the time when I'm finding the minimum spanning tree, because Kruskal's algorithm is about 20 lines more than this. I don't want to write that much. So some other common algorithms, I'm going to go through them. I'm not going to go through all their implementations because that would be a long time to go through. But Dijkstra's is a very common algorithm. You may have heard of it, you may not have, but you probably will if you're a computer scientist. It finds the shortest path from one source to all of the other nodes. So not just from A to B, but from A to every other node in the graph, it finds the shortest. There's a little GIF here kind of demonstrating what the algorithm does. This algorithm is commonly used for like pathfinding in maps because you need to be able to find all of the distances, right? And so an example problem would be, given a graph of cities with travel times, find the shortest time from a starting city to every other city in the graph. So if you see something like each other city or every other, it's probably going to be pointing you to an algorithm like Dijkstra's. because this is the algorithm that finds the shortest path between one node to all the other nodes. So the Bellman-Ford algorithm, again, I have a GIF here. This one's fairly complicated, so I didn't want to go too into the weeds with this one. But this is like Dijkstra's algorithm, but it handles negative weighted edges, which sometimes can happen depending on the implementation. It really doesn't happen all that much from what I've seen, but it's always possible. Like for in the example I gave, where you have a currency exchange network where maybe you actually gain money from going from one node to the other instead of losing it, so that you would have a negative, which would actually add to your total value. So that can be an example of something that you would need to implement that. The Floyd-Warshall algorithm is one that, again, is not incredibly ubiquitous. It's not used very often, but it is important to understand it because it's like Dijkstra's, but it's not just from one node to all the other nodes. It's every pair of node to every other node. So if every single pair, you're able to find the shortest path between them, which, as you would guess, is a very computationally expensive process. It's the number of vertices cubed is the time complexity, so it's only really suitable if you don't have all that many vertices to work with. But sometimes you do need to use it, like in this example problem I gave. I've come across one like this where you need to calculate the shortest travel time between all pairs of cities for whatever reason. This one's fun because the name for it is actually an acronym, DSU, the disjoint set union. It's also called union find. So in this GIF, it's actually an implementation of Kruskal's algorithm using the union find algorithm. So the Kruskal's is on top, it's finding the minimum spanning tree, and the union find is on the bottom here. And a union find algorithm is mostly necessary to implement Kruskal's, which is why I didn't want to write it. But basically, it manages a set of elements partitioned into non-overlapping subsets. So this is very helpful for if I need to find out if two elements are in the same connected component. It's not going to tell me how far away they are. It's not going to tell me any extra information other than the fact that they are or they are not in the same component, which for some problems is helpful. If, for example, I have the check if adding an edge between two nodes would form a cycle, because you know it won't form a cycle if they're already connected in the tree, but if you connect it, it might form a cycle. So that's helpful for that. So the actual hard part about graph problems isn't implementing the algorithm, it's recognizing when you have a graph problem in front of you and what algorithm you need to do to implement it. So I have a problem on Caddis. I can open it here, hopefully. Maybe not. Maybe not. So this was one that I was doing just the other day, and it's zoomed out for some reason. But another thing you'll find with competitive programming is they like to be very verbose for no reason. Most of this is garbage that does not matter, but they give a shout out to South Dakota, so that's kind of cool. But the actual important part is the input down here, where basically you're given a bunch of pairs of words. So in this case, we can, the, work, people, it, out, the. Those are the pairs. And the letter pairs above it are a list of letters that can be turned into other letters. So C can turn into T, but the important thing here is that T cannot turn into C necessarily. I can turn into R, K into P, so on and so forth. And what you're supposed to do is, can you letter by letter turn the first word into the second word somehow using some number of steps. So it might not be immediately obvious how this is a graph theory problem, but it is indeed a graph theory problem because you can represent the problem as, if I can pull this up, you can represent it as a graph. So I've written out a graph here where the nodes are the letters and the connections, the edges are showing that you can turn one into the other. So in this, you can turn C into T, you can turn T into E, turn T into F. And again, like this is directed, so I can't turn F into T. And this is really helpful because for that problem that we were looking at, if I just go letter by letter, like if I want to turn it into O, I just have to see if in the graph I is connected somehow to O. And then I need to see if T is connected somehow to F. I don't care how many steps it takes to get there. I just need to be able to tell if it's there. So what I used to implement the solution for this was a depth first search, where I would just start at the first letter and then keep searching until I found the letter. And if I hadn't found it before the algorithm stops, that means that they're not connected and I can't turn that letter into the other one. So that's this using letter transformations is something that the writers of competitive programming problems like to use for some reason. I guess it's just an easy one to use. So I have a little slide here on how do you recognize graph problems. The text is a little small, but basically you're going to have entities with relationships. These can be the nodes, such as cities with roads, people with connections between them, or letters with transformations like in this last problem. And another characteristic of a graph problem would be a reachability or connectivity question. Can this entity reach another entity? Another characteristic would be whether there's a path finding question that you're being asked. What is the shortest path between two entities? And then also cycles is going to be another common one they're going to ask about. Are there loops or are there isolated clusters of nodes? So keywords like reachable, connected, transformation, and shortest path are all going to be, it's not necessarily a rule, but most of these are going to be pointing you towards a graph theory solution for your problem. So as far as contests goes, you're gonna have to worry about the time complexity because they only give you a certain amount of time to run your solutions. So you have to consider how many nodes you're being given and how many edges you're being given, and what algorithm you're gonna use, because I can't just use the like the Floyd-Warshall algorithm, which is v cubed, because that is gonna be way too slow if I have 1,000 nodes. The best tips I can give you for optimization are going to be know your algorithms and use efficient data structures. If I try to implement prims without a priority queue, I'm going to have to keep looping over to see what the next smallest one is. But if I use a priority queue, it just always puts it at the front, so that's easy. And you also want to avoid recalculating things if it's not necessary. If I already know how far away A is from B, I don't need to recalculate that. That's something that can be stored. So a little bit about input processing. So the standard input formats are the ones we talked about, right? We talked about the adjacency list. We talked about the adjacency matrix. The only thing you'll have to worry about is if you have a weighted graph, you'll have to worry about reading in the edge weights too. So it's not as simple as just reading in two numbers and putting them in their place. In Python, I use input.split to split input exactly how it sounds. And in C++, a big tip I can give you is to use this line here, standard, in the standard namespace, in the iOS-based namespace. Using the sync with standard IO to false means that it's not, by default, C++ tries to sync standard input and standard output, but that actually slows things down a lot when you're trying to read in standard input. So making it not do that is super important if you have to read in like 1,000 lines, which sometimes you end up having to do because the people who write the questions are mean. So some common pitfalls. Um, these algorithms I talked about, not all of them are going to give you the right answer if you have a disconnected graph. Some of these rely on having a fully connected graph, which is not necessarily guaranteed depending on the problem description. You'll have to worry about self loops too, because in some graphs, a node can be connected to itself. I didn't talk about that because that's not very common, but it's technically possible. You'll have to worry about that. This could throw off something like cross goals because that self loop might be the lowest next weight, and it'll choose that when in reality it doesn't need to because it already has that node. Then for algorithms that require like acyclic graphs, meaning that there's no cycles, you'll have to add something like a visited list to check if you've already visited a certain node, because you don't want to have to keep going back, and that's just going to end up giving you an error or a recursion depth exceeded error. So some tips for practice. I personally use some templates for my graphs and for depth first search, breadth first search, and a minimum spanning tree problems, because I don't want to have to remember, oh, how did I implement that? I just have it written down on a little cheat sheet and I can just re-implement that. It's a lot easier than remembering every little intricacy of the algorithm. So like I said, recognizing certain patterns that fit the algorithms is going to be important too. If they're asking about finding the how far away like two layers is, right? How many nodes are only two layers away from a certain node? You know that, oh, I know that layers is associated with breadth first search, so I can just do a breadth first search, but only two layers deep, and I can count how many nodes there are. So that's something that just understanding the wording and doing some practice with problems is going to give you some help with. And also, always test your solution with edge cases, because they definitely will put edge cases in the test that you're being given for the problem. If they tell you that there's going to be at minimum one node and at maximum 1,000, they're going to put one in there that's one, and they're going to put one in there that has 1,000 nodes. So you want to test it out with the edge cases, because a single node graph, if your algorithm can't handle when there's just one node, you're going to end up having a problem, because they're definitely going to give you a problem. They're definitely going to give you a test case with that. Again, so if they're giving you something like a complete graph, which means that all nodes are connected to all other nodes, that could end up being a problem too if your algorithm is too naive and it ends up taking a really long time. So some recommended practice problems I have. So on this website, cses.fi, they have a really good problem set that has a bunch of graph theory problems, which is going to be, a lot of it's going to be exactly what we talked about today: depth first search, breadth first search, minimum spanning tree problems. So if you go through there and you work on those, you'll definitely be prepared for any graph theory problem that comes your way. And I have these 4 practice problems on Caddis that I would recommend. None of them are particularly difficult, but they are implementing the graph problems or the graph algorithms we talked about. So single source, shortest path, non-negative weights. Can anybody tell me what that would be? Anybody tell me what algorithm we would use for that?
Dijkstra's?
Yep, exactly. Because Dijkstra's, like we talked about, finds all the shortest paths between a single source and all of the other nodes. So that's exactly what we're going to want. Reachable roads is another problem. That one is pretty much exactly what you would expect. It's going to see if a road is reachable. Yeah, there's a minimum spanning tree. I wonder if you can tell what that one's going to be about. And then all pairs shortest path, that is also going to be pretty obviously one of the algorithms we talked about. It's going to be the Floyd-Warshall algorithm. Yeah, so that would be the problems I would suggest working on. Most of them aren't going to be as obviously graph theory as these problems. All of these are, like, especially the single source shortest path, non-negative weights. It literally tells you exactly what you're going to be given. So it's pretty easy to tell what algorithm you're going to need to use. But for the most part, they're not just going to give you a question like this, just implement Dijkstra's. It's going to be more nuanced than that. And you're going to have to interpret what they mean and what they want. So are there any questions about any of these graph theory things? Yeah. Sure. I can pull up a graph theory problem. So how about we actually solve this one together? So first thing I'm going to do is start coding. So what we want to notice about the input is what it's giving you. So it's going to give you an M and an N, where M is the number of translations and N is the number of word pairs. And then so the next M lines are all of the translations, and the next N lines after that are all of the word pairs. So first what we're going to want to do, actually I'll open VS Code so I can actually zoom in and make it a little easier to see. So first what we're going to want to do is read in the N and the M and all of the extra stuff. So I'm just going to duplicate my screen so I don't have to keep looking up. First, I'm going to read in N and M. So that's going to go like this. Because there's two different numbers coming in, I'm going to use a map if I can type properly. And my computer will autocomplete it for me. But that's how I read in two numbers or any number of numbers on a single line. The map function in Python is super helpful. Then what I'm going to do, actually going to get a chair. Is definitely going to be too short. Awesome. Then what I'm going to do is I'm going to read in the next M lines of numbers. So character 1 and character 2 is going to be the translations. So I'm also going to want something like a dictionary. So at the top, I'm going to a default dictionary is like a dictionary where you have key value pairs, but if you try to access a value that is not already initialized with access a key that is not already initialized with values, it's going to default to whatever type you give it. So I'm going to declare a translations dictionary, which is the default dict of a list. So if I try to access an element in the translations dictionary that is not already in there, it's going to just default that with a value of an empty list, which is going to be very helpful because I don't necessarily know if a letter is already in there. So thankfully, VS Code loves to autocomplete stuff for me, so I can just translations. So this line, what this does is I take my translations dictionary and I give it the key of char1, which is the first character I read in of that line. And to that value at translations, I append the value of character 2. So that's going to look something like, if I pull up a whiteboard, So that's going to look something like, if I'm reading in a C and a T, my dictionary is going to look like C pointing to a list with T in it. Then the next time I read in something where C is the first character, it's going to append that letter. So if I read in a CF, my dictionary is now going to look like C, which is the key, pointing to the value of a list of T and F. So this is the adjacency list we talked about. This is maintaining a node, which is my value, and all of the nodes that are connected to it, which is my, well, actually my key is my node, and my value is all the nodes that are connected to it. So that's the adjacency list that we talked about. So I've read in all of the translations. See, it's trying to get me to autocomplete it to have an undirected graph, but that's not what I want. I want a directed graph because the first letter connects to the second letter, but the second letter doesn't necessarily connect to the first. So next, what I'm going to want to do is read in the next n numbers, if that was indeed the correct order that it gave me. M is a number of translations and n is a number of word pairs. Fantastic. Okay. So word 1 and word 2 are going to be the two words that I'm working with. And VS Code generously auto-completes that line for me, where I'm just splitting it into two different variables, word 1 and word 2. The first thing we're going to want to check is what is it expecting for the answer. So it says two words match if they're the same length and if each letter of the first word can be turned into a corresponding letter of the second word by using the available translation 0 or more times. So what's the first thing we should check then to see if one word can be turned into the other? The length. Yep. So if I want to check, so if length of word, perfect. That's awesome. Thank you, VS Code. If the length of the word 1 is not equal to the length of the word 2, I know for sure I can't turn it into the word 2 because I'm never going to have enough letters to turn it into. So I'm just going to print exactly what it wants, which is just lowercase n-o. And then I'm going to continue, and the continue keyword means just jump to the next iteration of the loop. And then what I'm going to want to do is define a function to search for two letters, because now I know that they are the same length, which means it's possible that there is a way for them to be to turn one into the other. So wow, VS Code is really being helpful today. So the zip function, like it says here, it yields n length tuples, where n is the number of iterables passed as the positional arguments to zip. So what it's going to do is it's going to take my two words. In the case of can and the, it's going to make a new iterable where it looks like CT, then AH, then NE. Because that means that I can just automatically pair them off without having to worry about using two different pointers in the list. It just automatically zips them for me. So it tried to autocomplete it, but that's not necessarily true because it thinks that what I'm trying to do is just check if it's in the neighbors, but I need to check if it's in any of the neighbors of its neighbors of its neighbors, right? I need to check everything. So I'm going to need to implement a depth first search. So it will take, I'm not going to let it autocomplete for me. It's going to take a graph. It's going to take the starting node, and it's going to take a visited set. So the easiest way to do this is probably just going to be to go look back at my depth first search implementation so I don't mess it up. It takes in a graph, a node, and a visited. It adds the current node to the visited. So what that's doing is I'm at this node. I know I visited it. That's perfect. Then, man, it really wants to autocomplete properly for me, but I'm not going to let it. Then looping through all of the neighbors of the current node. So in the case of if I pass in C as our node, it's going to loop through T and V and F. It's going to loop through that list. And then it does indeed autocomplete there. So what this does is it's actually searching it, but I need to also check if the node I'm at exists in it, right? So something I'm going to have to do is add another argument here, which is the end node, which is what I'm looking for. And then do something where I'm checking if the neighbor is equal to the end node, and if it is, then I can return true because I found that node in the in my search. Now, all I have to do is get rid of the incorrect autocompletion here. Then, if caps lock, if the well, first I guess I can check, yeah, if char1's not char2. Then, if passing in the depth for search, translations is my graph, character 1 is my first argument, an empty set is going to be my my third argument, and the final argument is going to be my end node, which in this case happens to be the second character I'm looking to see if it reaches that eventually. And this this line here basically DFS returns a Boolean, and have to make sure to return false here. That could have been a problem, but basically I'm returning false here because if it never reaches this line here where it returns true, that means it just has to return false because it's already visited it. So this line here, basically, if DFS returns true, then that means that I can indeed reach them. Actually, what I'm going to do is, because I'm checking for all of the characters, so I need to make sure that once I hit one character that can't turn into the corresponding character in the next word, that I immediately break out of it. I need to print no, and I need to break out of this for loop here. And then I can just return true here, because it's only ever going to reach this line. Well, not return, I need to print yes. It's only ever going to reach this line if it never reaches the no line, right? So if it ever reaches the no, it's automatically going to break out and it'll ever print yes. But it will reach this line eventually if it never reaches the no line. So we'll do a quick test here to see if this is the correct answer. But can anybody think of any edge cases I'm missing? I can't see anything. No? Then we'll give it a test. I'll take this input, run the program, paste it in. Oh, great. Looks like we have an error. Missing one. Oh, awesome. Never passed back in the end here. All right, hopefully that'll work now. So we can see the answer is yes, no, no, yes, yes. Okay, and it messed up the printing. Run it again. So did it not read far enough? Interesting. Oh, I've switched these around. M comes in first. So it is getting it wrong. That's awesome. So looks like it's printing out yes, 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 no, 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 which is not even the correct number of things it should be printing out. So let me see if we can do some debugging here and figure out what the problem is. So is it reading these in properly? So what we can do is print M and N here to see if it at least can tell me what those are. And it does indeed think that M and N are 9 and 5. So next what we can do is we can print the translations here and make sure that everything is matching up. So my translations look like C to T, that's good. I to R, that's good. K to P, yep. O to C, yep. R to O, yep. T to E and F, yep. U to H, and W to P. So it looks like my translations list is also correct. So next thing is, what can we observe here that could be an issue? What's that? My guess is maybe it's having an issue here. Well, that should just work. Okay, so I think what's going on is it's printing this yes even when it shouldn't, because it, as soon as it breaks out of this, it's printing yes. So we're gonna have to add something to check it, right? So I'll call it check, and I'll say it's true to start. So I can set check to false. Then if check, meaning if check is still true, then I can print yes. And hopefully that was the issue. So it prints out yes, no, 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 no. Awesome. What's going on here? Maybe, not exactly sure what the problem is here. I do have a solution to this, so we can just see what the problem might have been. Looks like I used depth first search for this the first time, but that shouldn't really matter. Yeah.
It transforms from I to R.
Mhm.
Then there's also another transformation from R to R.
Yeah, it should handle that with the depth first search, but maybe it's not handling that properly. Interesting. So I'm not exactly sure what the problem is, but Hmm. Yes, maybe it's just a problem with this not needing to be there. See if that was the issue. That's even worse somehow. Interesting. So, looks like we're out of time. I can try to figure out what the problem is. I'm not. Looks like the only difference is that I'm not printing them right away and I'm just printing it to a results, but there's probably some nuance in here that I'm not understanding. Yeah. Yeah, sorry about not being able to get that, but this should theoretically work. Building a list of nodes or a graph where you maintain the connections and you search to see if you can find the specific node that you're looking for. In theory, this should work. There's probably some edge case, which again is why some of these problems can be a little annoying. And also why I don't tend to actually implement depth first search or anything myself. I usually have a format or a template for that and I just type it out. But yeah, so that's what I would recommend is not doing it yourself because as we see here, it ends up being a problem.